So divisibility by 5, again, usually it's done in the same two ways. One, you write down the the tables of 5, you look for a pattern, that's one way of doing it. And the other way is again to look at a number, let's say a 3-digit number, the hundreds, tens and ones, and show that divisibility by 5, what it means. So again, as you write down the numbers, here the pattern is fairly straightforward. You just have to look at the ones, and you get 5 and 0, and 5 and 0, and 5 and 0, and so on. So generally this is enough to convince the children that all that matters is the ones, and the ones are either 5 or they are 0. So here, as we can see, 2 is multiple tens, 5 is multiple hundreds, and so on. And if you take a 10 is divisible by 5 already. So it doesn't matter how many tens you have, you will always be able to put it as 2 rows of 5. So the tens and hundreds and thousands and 10,000s, since they are all divisible by 5, don't need to be taken into account, and the only thing to be looked at is the ones. And this is why when we are getting the pattern, the ones are either 5 or 0, it's divisible by 5, or it is not. So divisibility of 11 rule, again we know the rule. So usually you add all the odd digits and you subtract it from the even digits. So 2 plus 3, if I subtract from 5, either if I get 5 or a multiple of 11, it's fine. These numbers are divisible by 11. So here these two add up to 2, and these two add up to 2, so they subtract out nicely. Same way, this is 5, and this is 6, and this is 6, so they subtract out, and you get a nice 0, or you get 11, or a multiple of 11. These are all divisible by 11. So the question is why? Okay, so let's look at it just intuitively. So if I have a number that's a multiple of 11, that means there is some number that I can multiply by 11. So 11 is 10 plus 1, so it sort of kind of makes sense that there is a number and then it is shifted by 10 and it's added to itself. So there's some combination of the odd numbers and even numbers, maybe results in subtraction being 0 or 11 or something. But the reality is when you actually add the numbers, the digits add up and all kinds of things happen. So this is not really rigorous. This is just like an intuition that there must be a value and a shifted version of that value, which sometimes could be neat to see, but many times we won't be able to really see it. So the rigorous proof, so to say, is very curious. And the curious thing is that when you have 1 and you take a mod of 11, then of course 1 is alone. So 1 will, you take 0 times 11, the remainder is 1. So this is straightforward. Now when you take 10, of course again 10 is not divisible by 11, and you will have a remainder of 10. But another way to look at it is, if you look at the mod arithmetic, as you would have needed 1 more in order to become a multiple of 11. So you can also think of it as minus 1. So every 10 that I divide, I needed 1 more. Every ones I divided, I had 1 more. So now every hundreds I divide, I get 99, so I have 1 more. Every 1000 I divide, I need 1 more. Oh, these are all ones actually, so I don't need to do this really. I can use black down. They're all just ones. Each of them is resulting in a 1 and a minus 1, and a 1 and a minus 1. And this pattern repeats. So this means that when I have a number like this, when I'm dividing the 4s by 11, I'm going to be left with a remainder of 4. But when I'm dividing 40 by 11, I'm going to need 44. So I'm going to be needing 4 remainders. And if I take 100, then I'm going to have an extra 1 because of 99. When I go to a 2000, I'm going to need 2 more to complete, and so on. So that's why when we add the alternative numbers and subtract it, and that gives you either 0 or a multiple of 11, then we say that the number is divisible by 11.